We are considering star connected source, that is obvious. So we said in the last session itself, this is a source which is connected in star fashion or Y fashion. This is the load. So this is also connected in star connected load. I am considering as of now both are star connected. Load is star connected, source is star connected. And I will try to follow this kind of notation. For source I will use E letters. So source is inducing the EMF, so induced EMF I am trying to represent with E. For the load I am trying to represent the voltage as V. So R phase, this is one of the single phase, it look like this. So let me put up over here as like this. So this is one dash terminals of the load previously which we used to say. This is two dash of the load. This is three dash of the load. How we connected these three individual single phase loads is star fashion. And the starting terminals, those are 1 2 3, are connected to the source terminals which are of, let me put up over here, this is of R, this is of Y, this is of B. So we connected to the generator three terminals R Y B. And one more thing here I want to point out, that there is a common terminal which we call generally as neutral for the source, and there is also common terminal for the load which we call this also neutral, but let me represent this as a small n. So source neutral I am representing capital N, load neutral I am representing small n. And generally in whatever we see in real time is that, so these neutral terminals will be extended and we call this as N. So R Y B and N, and this neutral terminal will be connected to the load neutral terminal also as like this. So now see that it is a bare simple neutral of the source small n, and the load, sorry, source is capital N and the load is small n, are joined by a conductor, or joined by a conductor. We will understand why we connect this kind of thing, what signifies this, so little later. So as of now I want to introduce some terminology. The terminology is phase quantities. Phase quantities. Phase quantities is nothing but it may be phase voltage or phase current. So first let us see what is the phase current or phase voltage. Let us say phase voltage. Here we know this, see, three phase generator is formed by the help of individual single phase generator. This is one generator, so single phase generator. So we can call this as one of the phase of the three phase, one of the phase of the three phase. Similarly, other two. Now the voltage appeared or produced by this corresponding single phase generator is called as a phase voltage of three phase system. So the voltage of the voltage of the voltage of the voltage of any single phase, instead of generator I will call single phase coil, the voltage of any single phase coil. So here voltage is nothing but induced voltage, that you should understand. For generator it is induced voltage. Now can you see here, what are those voltages? For coil 1 the voltage induced is ER, so can I say ER is one phase voltage. Similarly EY is another phase voltage. Similarly, EB is another phase voltage. So these are the phase voltage magnitudes. So remember that these are not phasors, these are only voltage magnitudes. These are voltage magnitudes, and you should understand that these are RMS values. These are RMS values. It is defaultly understood. The capital case letters are mostly RMS values, which are steady state in nature, constant. Right. So I want to point out some more observation here. If you see the one of the coil, generally we called previously this as coil 1, coil 1. See where coil 1 is connected. Just I want to demonstrate only coil 1, then you can understand coil 2 and 3 also. Where coil 1 is exactly connected. Can I say at the terminals here between R and N, between capital R and N, this one of the coil is connected? Can somebody say yes or no? Yes, yes. So this coil 1 is basically connected between the terminals of R and N. R and N. So now we can call this as V, or let me use the same notation, E R N means R phase to neutral is nothing but coil 1. R phase to neutral is nothing but coil 1. Voltage is equal to ER. ER. Voltage is equal to ER. Similarly, can you identify these things? Y phase to neutral, its corresponding voltage is coil 2 voltage. How much is the coil 2 voltage? EY. Similarly, coil 3 voltage is EB to N. EB to N, which is equal to EB. So these are the notations which we adopt hereafter. That is R to neutral, or Y to neutral, or B to neutral is called as a phase voltages. Is this clear? Yes. And of course, until unless I want to, means if until unless I represent with phasors, you should understand these are only magnitudes. I am talking only about these magnitudes. I am not including phasors here as of now. I will introduce phasor little later. Now, one more thing is, see, if we have one generator, then it is producing the current. The current will be outward the generator terminals like this. So this is the current which is coming out of this single phase coil 1. Similarly, for second coil, the coming is coming out of this coil. So this is again next coil current, coil 2 current. Similarly, coil 3 current is current coming out of this wire. So now hereafter we can call this is R phase, this is Y phase, this is B phase. The current produced by this coil is referred as a phase current. Phase current. So I will show here as like this. IR, here as IY, here as IB. But at the terminals outside of the generator, try to understand this very carefully. Let me put up this thing. So this is the generator. Left side is the internal portion. Right side is the external. Now this right side external corresponding currents will be referred as generally lines. These are lines. What are the lines? R phase line, Y phase line, B phase line. So the currents are referred as R phase current, line current, Y phase line current. Try to understand the terminology. B phase line current, R phase line current, Y phase line current, B phase line current. If you want, you represent L, YL, BL. For your simplicity or for understanding. Later on, I may not use these many notation, just simply I will try to put up directly. Now try to observe that this current produced by coil 1, which is phase 1, is equal to this line current. Why? Because there is no splitting path over here. This entire current IR is passing through these lines also. What are the lines is? Just this portion, generally we call as the lines. Let me highlight that. External to the generator, generally referred as a lines. This portion is the line. We call transmission line. You will see outside, so there will be some transmission lines. So those are used for transmitting the power. So here, internal to the generator we call as a phases. Once external to the generator line wires are there, those wires we call as a lines. Those wires we call as a lines. Now here try to observe these line currents are equal to phase currents. So let me write here phase currents first. Phase currents. What are the phase currents? The currents produced by the individual coils. Currents produced by individual coils. Which are coil 1, coil 2, etc. So what are the examples? Here you can see the diagram. IR is the coil 1 volt current, IY is the coil 2 current, IB is the coil 3 current. These are called as a phase currents. And now let me put up here itself line currents. These terminologies are very important. Phase currents are different from line currents in some situations, but here it may be matching. The currents flowing in the lines of the system. System means it may be transmission system or it may be distribution system, depends on the consideration of the network. So the currents flowing in the lines of the system. I told you what are the lines. Lines are nothing but external to the generator and external to the load. So excluding those internal parts of the generator and so load, just there will be some wires. So you can see even in your home outside there will be like poles, conductors will be there. Those conductors you can call as the lines. So as of now, though it is not very accurate, I will introduce later on some more terminology, but you can imagine that is equivalent to lines. So lines are these external to the generator. And here in case of star connected configuration, there will be some default advantage that the current flowing internal is same as that of the current flowing through the line. That is what the advantage. This is very important observation. So the line current IRL is equal to phase current IR. Similarly, the line current IYL is equal to the phase current IY. The line current IBL is equal to IB. So try to understand that. Here let me put up in terms like in star connected configuration, in Y configuration, line current is equal to phase currents. This is very standard definition. You refer any book, this follows. So in Y configuration, line currents is equal to phase currents. And we want to introduce one more thing, line voltages also. That I want to discuss in this way. Now, what are the lines here is that, just let me point out, generally, if you consider in the transmission system or in the distribution system, this neutral may or may not exist all the times, may or may not exist all the time. So that's why the line voltages are defined between the lines of the single phase generators. What are the single phase generator terminals? Let me know first clearly from your side. What are the single phase generator terminals in this combination of the three single phase generators are here? What are the terminals? RYB. Okay, that should be very clear to you. N is not any generator terminal, it is like common terminal. Don't say N is generator terminal. N is common terminal. R is one of the single phase coil terminal, which is R phase. Y is second coil terminal, which is Y phase. B is third coil terminal, which is B phase. Now, the voltage between any of these two phases, it may be as like this: R2Y, R2Y. Let me represent here. So, R2Y, I am putting over here. R2Y. This is one. So next is Y2B, second. Next is B2R, B2R, or B2R means it should start from B. So arrow should be pointed towards B. Yeah. R2Y, Y2B. So this also arrow should be little different. Whichever we pronounce first, so that side should be the arrow. That is, I am saying Y2B. So Y side should be arrow, other side should be non-arrowhead. Now let me write these voltages also here clearly. This is E, means induced voltage of the generator, between which terminals? R and Y. This is the notation hereafter we follow. RY means voltage between R terminal and Y terminal, where arrow is pointing at the starting one. What is that? R. This one, R. This notation is important. Similarly, Y to B. So E, Y, B. Carefully observe these notations. These are very important to be followed throughout your career. One more is B to R. E, B, R. E, B, R. So let me write these line voltages first. So line voltages. So these are the voltages between any two lines of the generators So generator has three lines now. We are talking in the perspective of three-phase generator. In three-phase generator, how many lines are there? Lines is nothing but the corresponding number of single-phase generators. How many single-phase generators are there here? Three. So each one is connected to one line. So line 1 is corresponding to R phase coil. Line 2 is corresponding to Y phase coil. Line 3 is corresponding to B phase coil. There will be a neutral line, but that will not be always existing. That may or may not exist. That we see later on. So the line voltages are between any two lines of the generator. The voltage between any two lines of the generator. Let me write completely. Voltage between any two lines of the generator. For example, as like this. So between R and Y, we could represent as E suffix R Y. What does it means is that, try to understand carefully, that this R is at positive with respect to Y. That should be very clear to you. Whichever first we write in the suffix, that is at the arrowhead. Other is non-arrowhead. Arrowhead is equivalent to positive. Non-arrowhead is equivalent to negative. Like that. Similarly, so E Y B means Y to B. Similarly, E B R. You can consider in reverse also, nothing wrong in it. As like this, E B Y, E R B. It's your wish, but this is some kind of systematic pattern we are following. First to second, second to third, third to first, like that. If you assume coil 1 is R, coil 2 is something like this. This is R is equivalent to first coil, Y is equivalent to second coil, B is equivalent to third coil. Now you can move on like R to Y or Y to B, then B to R, like this. So we can call 1 to 2, 2 to 3, 3 to 1. So RY, YB, BR. It's your wish. Now let me move on little bit more systematic way, that as here just I want to point out some things. That is, first let me put up the phase voltages. Phase voltages. And what kind of phase voltages is that? Balanced. Balanced. Now can anyone tell me what is balanced? Quickly. Yes, exactly. Yes. So now I will assume like this: ER phasor is equal to, all magnitudes are equal, simply I will call E. So similarly, I will add the angles a little later. See that EY is equal to magnitude E, EB is equal to magnitude E. All three are having same magnitudes. First thing. Other thing is that I am considering this as positive phase sequence. Positive phase sequence. That is nothing but, you can call 1, 2, 3 phase sequence, or RYB phase sequence, or ABC phase sequence also. If you consider R is equivalent to A phase, Y is equivalent to B phase, so B is equivalent to C phase, so you can consider any of these notations. So what does it mean is that, like this, for example, if the observer is sitting on the R phase, means that is our reference. If observer is sitting on the R phase, that is our reference. This is what the reference, where the observer is sitting on the R phase. So this is ER phasor. Now once you know the observer where he is, means this is the reference. So let me put up this as reference. Once you know this, where is the observer, and once you know the nature of the voltages are balanced and positive phase sequence, after R, which phase should come? Y. It is in the positive phase sequence, so after R it should come as Y. So Y should be delayed by an angle of minus 120. Y should be delayed by an angle of minus 120. So similarly, so you can see what will be the B phase. So B phase will be further delayed by 120 degrees. So you can write this as minus 240 minus 240 or plus 120. I'll tell you once again with the phasor diagram also. This is E at an angle of plus 120. Now you can see if you put up these things in the phasor diagram form here. I am not using color coding, just assume that these are colors. Now try to understand that. So this is lagging at an angle of 120 degrees. From this the B phase is lagging further 120 degrees. But together from the reference, it is lagging 240. That's why we are getting 240. Is this clear? So this is the B phase, EB. Now, where is the EB existing? If you move in clockwise, that should be negative. So how much is the angle? 240. If you move in anti-clockwise, how much is the angle? 120. But anti-clockwise is plus 120. So that's why we can write this as plus 120. So hereafter, people will say that balanced supply of magnitude some, let us say 440 volts or etc. So you can understand from this given information, if it is a positive phase sequence, you could produce remaining voltages. These two voltages can be so defaultly drawn on your own. They won't give all the things. What they will give is just I am trying to write here. I am trying to realize. Later on they'll say that like this. So three phase 440 volts 50 hertz positive sequence, or they will say RYB sequence system they'll say, that's all. Then based on this I could produce the three phase voltages as like this. They didn't said anything balanced. So if it is not specified anything balanced, it is understood that it is a balanced system. If it is unbalanced, they will specify. If it is balanced, they may or may not specify. So this given value is line voltage, so which is equal to E. E is equal to 440 volts. It is understood by this, which is RMS value. Now I can write ER is equal to, I can consider R as a reference or Y as a reference or B as a reference. It's your wish. So means more possibly, so we will choose the R phase as reference. And one more thing I want to point out that, or just let me stop this over here. Why? Because I want to introduce a little bit more. Then I will come up this kind of pattern. So, but generally in problems or even in real time, all places peoples will show this kind of notation to describe the system. Three phase 440 volts 50 hertz RYB sequence or balanced or unbalanced. Here, so now with this assumption that the phase voltages are balanced positive sequence, I want to derive the line voltages. This is ultimate goal. What are the line voltages? See that. Now I know R phase voltage, I know Y phase voltage, I know B phase voltage. Can I get the line voltages? So for which just let me take up this diagram. Why? Because with the diagram way you can understand in better. So here let me put up the things. right. So now just try to understand and recap the basic Kirchhoff's law. Just I am, for sake of easy understanding, I am removing this neutral terminal. I don't want to concentrate on neutral as of now. So we have three terminals now. This yellow also I want to extend, this missing. This is what, the 2, this is 3, 1 2 3. 1 is R, 2 is Y, 3 is blue. So now let me write in this way. This is very important, that's why I am just carefully writing the things. Line voltage, line voltages. What we are doing is that we are deriving what will be the line voltages in terms of phase voltages. So later on we will see, if phase voltages are assumed, what will be the line voltages, if line voltages are assumed, what will be the phase voltages, when we discuss the numerical problems. But the relationship between these two are very important. So first, which line voltage I will be considering is that R2Y, R2Y phasor, R2Y phasor. Now try to understand, where is the R phase terminal, what is its voltage. So shall I put up like this? This is R phase, ER phasor, and just for your understanding I am putting only for this case EY phasor, magnitudes arrow pointing positive. Now this is the voltage between R2, R2Y. Let me write that also clearly. Here to here, E, R, Y. What does it mean? R side is positive, so where R side is arrowhead pointing, non-arrowhead represents negative. Non-arrowhead represent negative. That means Y we considered as negative. Now simple Kirchhoff's voltage law. I want ERY. Can I write plus ER minus EY? Why? Because this arrow is pointing plus. This arrow is pointing plus. So now see, from here to here, or whatever form you understood KVL, you write down. If I'll start here, I can write like this: plus ER minus EY minus ERY is equal to 0. Are you getting my point? If I start over here, I can move through the elements like this dotted line, and I reached at the same starting location with this path. In this path, what are the voltages? Plus ER minus EY minus ERY is equal to 0. This is minus, this is minus. Then can I write ERY as ER minus EY? Are you getting? ER minus EY. ER phasor minus EY phasor. Whenever we try to add up the things, don't add magnitudes. You will get wrong things. You should consider addition of the phasors, not simply magnitudes. Now, we already derived what is ER. Tell me, what is ER? We consider balanced, so its value is E at an angle 0. E at an angle minus 120. Check it in the above slide. In this slide, see, ER is E at an angle 0. EY is E at an angle minus 120. Now, can you simplify this? You can type directly in your calculator. You take the E common. What left out is 1 at an angle 0. Another is 1 at an angle minus 120. Or you can convert this into rectangular form, add real parts and imaginary part, thereby convert into polar form. but that much work is not required. You can type in your calculator directly this polar form notations. 1 at an angle 0 is nothing but 1 minus of 1 at an angle minus 120. Tell me the answer. Root 3 at an angle 30. Is that? Anyone got it? Yeah. So here is the very, very important conclusion. Root 3 E is the magnitude now. What is the angle is 30 degrees. So can I say ERY is the line voltage. Magnitude is equal to ERY, line voltage magnitude is equal to root 3 times of the phase voltage. Angle of this is equal to 30 degrees at 30 degrees at plus 30. We will plot the phasor diagram also little later. This is the magnitude. So that should be very clear to you. So let me write here if you want. Mod of ERY. What does it represent? Magnitude of the line voltage. So I will put up like this. EL. Line voltage magnitude is equal to EL. EL is equal to root 3 times of E. What is E? E is phase voltage magnitude. So if you want, you can create a notation for simplicity understanding as like this. Root 3 EP. P means phase voltage. EP. So the things, whatever we assumed, you should understand clearly. E means phase voltage in the previous notation. Some people may use EP also, nothing wrong. Try to understand that line voltage magnitude is equal to root 3 times of the phase voltage magnitude. Once you know phase voltage magnitude, you can get the line voltage. Or once you know the line voltage magnitude, you can get the phase voltage. Are you getting my point? If EP is given, you can say root 3 times of EP is EL. If EL is given, EP is equal to EL by root 3. Got it? Yeah. So this is very important. And now keep this expression aside. We will refer this expression again after deriving remaining two line voltages while plotting the phasor diagram. Okay. Right. So now similarly, just try to see this diagram Y to B. So just by visually looking at, you should write what is Y to B is EY minus EB. Are you getting? EY to B is equal to EY. Here is the plus terminal. Try to see that. Plus is over here. And this blue color plus is here. That means EY minus EB is the EYB. So now let me write that voltage also. EYB is equal to EY minus EB. Quickly tell me what are these voltages. EY is E at an angle of minus 120 and EB is E at an angle of plus 120 or minus 240. You use any one, you will get same answer. Similarly, EBR is equal to, so EB minus ER is equal to EB is E at an angle of minus 240. ER is E at an angle of 0. Quickly tell me what are all these. So this, yeah, at an angle minus 90. Very good. What about this? Root 3. I think here E is there, right? Root 3 E at an angle of 150. Now try to plot all these voltages, which gives a good significance. So I'll use the color. So this is the R, this is the Y, this is the B. These are phase voltages, try to understand. ER, EY, EB. Okay. So R is at 0. So this is 120 degrees lagging. This is further 120, together from the reference is 240. Now try to observe that. What is the ERYB or ERY? ERY is the phasor sum of ER and EY. Can I say this as like this? Generally, negative phasor subtraction will not be done. Instead of that, ER plus of minus EY means negative phasor addition. Now try to observe that where is EY and take negative of that. Negative of that can be plotted as like this. EY is opposite to this one, dotted line. Dotted line is minus EY. Let me point out here that this is EY. Visibility is very low. Try to follow me. This is minus EY. Phasor. Is this clear? So now ER is here, EY is here. Phasor sum of these is obtained by the drawing the line in parallel to the ER and EY minus EY. The diagonal will shows the resultant voltage, and this is the diagonal. So this diagonal shows the ERY. Now try to see that ERY angle is 30 degrees. This is what the 30 degrees plus 30. Similarly, EYB or EYB, right? Yeah. EYB means EY plus of minus EB. Where is EB? Take that negative value. EB negative means in this way. Now draw the parallelogram to get the resultant of EY and minus EB. Then the diagonal will give the resultant, which is E, this black color one, E, what is that? Y, EYB, right? Yes, EYB. What is the angle of this? Check it. EYB angle minus 90. See, from here to here it is 90. It is 90. Similarly, you can see BR. BR means negative R. So you take the negative R over here. So carefully observe. If you see all together, you may feel little confusion. So that's why I'm taking step by step clearly. So minus ER is this one. So minus ER plus EB is the EBR. So yeah, so this is minus ER. So take the parallelogram for this. Sorry. This is parallel to the minus ER. Now B, this is parallel to the minus EB plus EB. Then the diagonal of this parallelogram represents the resultant line voltage. What is that line voltage? Is that E B R. So how much is the angle made by this is 150 positive. So here to here angle is 150. Try to observe carefully. From where? From reference. This angle is how much? 150. These are very, very important, and on this phasor diagram I will put up some more conclusion points in the next class. Okay, that is, the line voltage is this one, phase voltage is this one. ERY is the line voltage, ER is the phase voltage. How much is the angle difference between line voltage and phase voltage? 30. Similarly, EY is the phase voltage, EYB is the line voltage. How much is the angle difference? 30 again. See, this EY is at 120, EYB is at 90. Difference is how much? 120 minus 90, 30. This is the 30. Similarly, EBY and EB is differed by 30 degrees. These are very important conclusions, and this phasor diagram is very, very important. All of you draw on your own these three voltages, which are ER, EY, EB first. Then try to find ERY, EYB, EBR on your own through the phasor diagram, this kind of diagram based on this. So you can understand many conclusions from this phasor diagram if you have a clear idea on this phasor diagram. Okay. So first what we started is that phase voltages, and we try to get the line voltages. Now we are looking for the relation between this line voltages and phase voltages. If any one is given, we can get other thing. That is what our ultimate aim. Okay. Thank you.